Hello, everyone. This is Ricardo Calaon, and this presentation is about the paper Optimal Actuator-Based Attitude Maneuvering of Constrained Spacecraft via Motion Planning Algorithms. First of all, let's define what we're talking about when we say constrained spacecraft. We are talking about a spacecraft that is subject to hard rotational constraints. Think, for example, of a sun sensor that whenever we maneuver the spacecraft, we want to be able to see the sun at all times. This is what describes a keep-in kind of constraint. Or think, for example, of a sensitive payload such as star tracker or a telescope, which at all times as we maneuver the spacecraft must avoid pointing at bright objects such as the sun. These first few slides will summarize the results or the main takeaways of some previous papers. First of all, the attitude sampling in MRP space. So one of the key concepts applying in this paper is that we are sampling the attitude space of the spacecraft using a three-dimensional Cartesian grid in MRP space. The reason why we use MRPs is that they are a minimal three-dimensional set. And also, it is possible to restrict the operational domain to the unit sphere without loss of generality, because a unit sphere is enough to, all the points within the unit sphere are enough to describe all the space of attitudes of the spacecraft. We sample the attitude using a three-dimensional grid where each node is connected to a maximum of 26 neighboring nodes. And this allows to define a graph which can be searched given an initial and a final attitude and a path planning algorithm. And here we can see what keep out constraints in the inertial space, which are shown in the figure on the left, map to an MRP space. So in the figure on the left, we can see 3 keep out zones in inertial space, whereas in the figure on the right, we can see what these constraints look like in MRP space. The little dot in the center represents the initial attitude of the spacecraft. And specifically, this problem will turn into a problem of moving that little dot in MRP space, avoiding the obstacles at all times. Another important technique that shows up in this work is the use of NURBS curves as path smoothing technique. With NURBS curve, or NURBS stands for non-uniform rational B-spline curves. And basically just think about glorified interpolation technique. Even though interpolation is one type of NURBS curve, it is possible also to define a least square interpolating NURBS. But basically the property that we are looking for here is that of a function that allows to take a series of discrete attitude waypoints and map them to a smooth and differentiable trajectory, which provides attitude, angular rates, and angular accelerations as a function of time. And this is a quick example of what I was just describing. Here in the figure on the left, we see the trajectory of the Bohr side, of the sensitive Bohr side of the spacecraft in inertial space, when the reference is given just in terms of a discrete series of attitude waypoints. And we can see that this trajectory is piecewise linear, but it presents sharp corners that would be hard to track accurately for the spacecraft. Whereas the plot on the right shows the trajectory that is obtained using NURBS curves to interpolate that same sequence of attitude waypoints, but what we obtain here is a smooth reference trajectory that doesn't have those sharp corners anymore. And last but not least, since we have effectively a graph that we need to navigate from an initial attitude to a desired final attitude, we need a graph search algorithm that is able to do so. The choice here falls on A*, which is both an efficient graph search algorithm in the sense that it minimizes the number of nodes that it needs to visit to compute a solution. And it is also optimal in the sense that if a heuristic function is defined appropriately, it allows to compute an optimal solution. In the previous work, the cost function used by the A* algorithm that here is defined as C0 is an integral of the controlled torque required to actuate the spacecraft over the trajectory, or I should say the integral of the norm of the controlled torque over the whole trajectory. We can see here that the controlled torque is defined simply using Euler's equation. So this is not actually the most accurate representation of the torque required to actuate the spacecraft. This is because this equation does not account for the fact that spacecraft are often actuated using reaction wheels. So reaction wheels are devices that have their own inertia that needs to be accounted for. And even more importantly, reaction wheels spin, and by spinning up or down, they can exchange momentum with the spacecraft, but therefore they also contribute to the control effort that is required to actuate the spacecraft, because with their own momentum, they can make that control effort bigger or smaller. So what we need to do is to define a better model to account for the reaction wheel dynamics. Obviously, the way to do so is by making our math slightly more complicated. The first equation is an equation that allows to compute the full inertia matrix. Specifically, the inertia of the spacecraft is added to the transverse inertias of the wheels, such that as the spacecraft rotates, it accounts for the inertia of the wheels as they rotate with the spacecraft. The second equation describes the fully coupled equations of motion, where we can see that the angular acceleration of the spacecraft depends not only on its angular rates and the inertia, but also on a term hs, which is the vector describing the angular momenta accumulated on the wheels, plus a term gs us, where us is effectively the vector or the array containing the control torques required to actuate the wheels. The equation that expresses such control torque for the wheels is provided in the last equation, and also this equation for us, if multiplied by the wheel speeds, allows to compute the power that is instantaneously required to actuate the wheels. So at this point, if we combine all the previous equations together, it is possible to obtain the equation that I'm showing here above, which allows to compute the derivative of the wheel speeds. Why is this important? This is important because in this application, the trajectory of the spacecraft is computed by the graph search algorithm and by the interpolating NURBS. So every trajectory is known as far as the spacecraft's motion. What is not known a priori is the equations of motion or the trajectory of the reaction wheels. The only information that we have in the beginning is omega 0, so the initial wheel speeds. But at that point, the speeds of the reaction wheels need to be integrated. So knowing omega dot as a function of time allows to accurately integrate the wheel's equations of motion. And here I'm doing so by means of a Runge-Kutta fourth order integrator, which works by defining the four coefficients K1, K2, K3, and K4 reported here. And the last equation defines how to calculate the wheel speeds at every new time step n+1 based on the wheel speeds at the previous step, omega Tn. This is a simple example of a trajectory computed for the spacecraft, where we can see that the sensitive bore side, the line in red in the figure on the left, is avoiding the two obstacles, and it's going from an initial to a final pose. And on the right, we can see the attitude as a function of time and the angular rates of the spacecraft as a function of time. And again, this is a product of the pathfinding algorithm and the spline curves. The thing that I want to stress out here is that for this specific case, we intentionally chose a rest-to-rest maneuver, which you can see from the fact that all the initial angular rates and final angular rates are 0. This is important because now we are looking at the integrated equations of motion for a system that has 3 reaction wheels on the left and a system with 4 reaction wheels on the right. And I would like to stress out the fact that in this case, we are assuming that all the reaction wheels start from an initial from initial wheel speeds equal to 0. Since reaction wheels are momentum exchange devices, there is no momentum or no torque provided to the spacecraft externally. So since all the torque that is exchanged is between parts of the same system, the total angular momentum needs to be conserved. We can see that this happens according to physics because all the final angular rates, both in the case with 3 reaction wheels and 4 reaction wheels, are 0. This means that since the initial angular momentum was 0, also the final angular momentum needs to be 0, and this is accurately verified by the integration of the equations of motion. So this is just to validate that the math is working as intended. At this point, it is possible to define 2 new cost functions. The first one, C1, is a torque-based cost function. It's very similar to C0, but in this case, we are integrating the norm of the controlled torque that is required to actuate the full system consisting of a spacecraft and a set of reaction wheels. And the second cost function is C2, is a cost function defined based on the power that is consumed to actuate the wheels. Specifically, since this is an integral over time of a power, it has the units of an energy. And here I'm showing some numerical results. On the left, we can see a case with 3 reaction wheels where all the initial wheel speeds are at 0, but the spacecraft has an initial angular rate directed along the z body axis. So we can see that all three path planners, based on the 3 different cost functions, accurately take advantage of the initial momentum of the spacecraft, and they keep following the initial movement of the spacecraft that goes from left to right. But we can see that the solution based on C0 is different from the solutions computed by using the C1 and C2 cost functions. Specifically here, the C1 and C2 optimal A stars produce the same solution. On the right, instead, we see that we have the same initial conditions for the spacecraft. Again, we have 3 reaction wheels, but in this case, one of the 3 reaction wheels has an initial wheel speed of 500 radians per second. And we can see in this case that, again, all 3 planners exploit the initial direction of the spacecraft. They don't try to go against it, but we can see that the 3 solutions computed using the 3 different cost functions differ from each other. They produce different solutions. And in these last few cases, on the left, we see a case with 4 reaction wheels. Again, the spacecraft has the same initial angular rate, and the 4 wheels have pretty random initial conditions. Again, we see that we're computing 3 different solutions. And the most compelling case, in my opinion, is the figure on the right, where, again, we have 4 reaction wheels. In this case, however, the initial angular rate of the spacecraft is directed towards the x body axis of the spacecraft. And we can see here that the cost functions C1 and C2, so the new ones, basically have the spacecraft steer downwards and then from left to right, whereas the solution computed using the old cost function C0 goes in the opposite direction. This is, I think, the most compelling case that shows where neglecting the dynamics of the reaction wheels of the actuators can produce a solution that is significantly suboptimal and significantly different from the solutions that are computed using more insightful cost functions. These tables are meant to show the cost computed for each cost optimal trajectory. So basically, we can see that for the first 2 cases that I discussed, each cost function yields the optimal solution with respect to that cost function. These are the same tables for case 3 and 4, or case C and D. And we can see that here there's actually an anomaly related to the cost function C2. And this can be noticed if we observe that the C2 optimal cost function, which is supposed to compute the optimal C2 cost, is not actually computing the trajectory associated with the optimal C2 cost, because the C2 cost computed for the trajectory obtained with the C1 optimal algorithm is actually better. I will talk more about this in the conclusion in the next slide. Whereas for case number 4, everything also went according to plan. So to conclude this presentation, it is possible to obtain a very accurate integration of the reaction wheel equations of motion by means of an RK4 integration. The newly defined cost functions C1 and C2 consistently perform better than C0, which neglects actuator dynamics. So this provides an improvement regardless of everything else. Some suboptimal behavior is occasionally observed. This is what I meant when I was showing that anomaly for the third case. However, this has been observed to happen near solutions that are associated with very similar costs. Specifically, in the previous slide, you could see that the error between the two solutions is about a 1.5%. So yes, this potentially exposes a flaw in the methodology, which will be further analyzed. It will be the object of future investigations. However, it exposes a flaw that happens between solutions that are very close to optimality. And this was all. With this, I'm concluding my presentation. If you have any question, feel free to reach out to me. Here's how you can do that. And thank you all for your attention, and have a great rest of your day.